Well, good afternoon, everyone. It's a big pleasure to welcome here among us Fabio. Fabio is an expert of supernovae and so evolution of high mass stars, also in the context of multi-messenger observation. And Fabio got his PhD in Naples and then moved to a postdoc position in Rome at the Supernovae of Monte Porzio Catone, right? And now he's back in Naples with an assistant professor position. So today, well, he's also head of a supernova group at the Rubin Observatory, and today he's going to tell us something about the evolution of high mass stars, supernova, and what we can learn from about stellar evolution from their stars.
Thank you. So, hello again, Fabio Ragosta, as Mario said. Now I'm working at the University of Naples Federico II. The goal of this talk is to not shading the light on the mystery of stellar evolution. I'm not at that point of my career, but just to stress how it's possible to use also supernovae to constrain the theory of stellar evolution, what we can say using supernovae about what we know, what we miss, and what we have to pursue to, of course, to understand better the stellar evolution theory. To do so, I'll go, if the slide go on. I'll go through some state of art of the supernovae. So what are supernovae, what we know about them, how we can study them, and what kind of information we can extract, both from a single event studying or from a statistical point of view. Then I'll try to stress the point that typically we study, we model and we interpret data considering supernovae coming from just single stellar evolution, but they are not always in a single system, and what would change in the studying of the supernovae event when we consider that progenitor are not just a single star, and then what we want to pursue from now on. So basically, a supernova is a last stage of a very mass star evolution. Typically, when a single star evolved through all its life, ended up with an iron core, then the iron core cannot ignite anymore the fusion reaction. So the only force that is at play at that point is the gravitational pull, and the outer envelope of the outer of the core start to collapse on the core. Once the collapsing star, the core reaches the maximum contraction. So at that point, the infallen material start to create like a shock breakout wave that interacts with the infallen material, starting reaction that produce a cascade of neutrinos. At that point, the density in the vicinity of the core is so high that the cross-section of neutrino is very high. So they interact with the material and push everything out, driving the supernova explosion. This is the frame that we use to describe the core collapse, what we know as core collapse supernova. So single stars that evolve to the point of a supernova event. However, it's not the only channel that through which we can see supernovae. There is another channel that involves binaries in which one of the companion is a white dwarf, or both of them are white dwarf. In that case, we speak about type 1a supernovae. The explosion mechanism is different. It's not the collapse, but it's thermonuclear runaway driven by the reaching point of the Chandrasekhar limit in the case of the overflow material of a super giant on the white dwarf companion, or the merging of two white dwarfs. However, in both situations, in both the cases, what we see is the energy radiating from the nuclear processes that form the cobalt and the nickel from the neutron caption in the ejecta region. So in the ejected material that is energetically excited by the explosion. So we can the energy budget of the supernovae can be divided partially in the gravitational energy, partially on the neutrino side. This is the higher amount of energy of the energy budget of the supernova, and just 1% is the radiation coming from the reactions. However, this is what we see is a true radiation that coming from the ejecta that we can study the different aspect of the stellar evolution of the progenitor, because if at early time the spectra show us the outer envelope composition, at later time we can see through the envelopes of the stellar progenitor. And studying the spectra, we can separate different classes. So the type 1 class that show no hydrogen in their spectra, with respect the type 2 class that show hydrogen in the spectra. However, type 1 have a subclass separation known as 1A that show silicon in the silicon emission in the spectra, and while type 1BC do not show any hydrogen, silicon, or helium in the spectra. So we can see just oxygen, calcium, carbon, magnesium, and so this is what driven the idea that this is just a schematic of what I was saying, an idea what are the progenitors of these classes of supernovae. However, we don't study supernovae just from spectra, but also analyzing the light curve. So how the photometry change over time, and also with respect to different classes, we can highlight different features in the light curve themselves. For instance, the fact that typically type 2 supernovae has hydrogen in the ejecta. If there is circumstellar material and if there is the ejecta will interact with the circumstellar material, there will be an ionization of the hydrogen in the ejecta that will re-emit in the optical band, and will actually stop a little bit the decay of the light curve, creating that the knee in the light curve that is due to just the reionization of the hydrogen. As I was saying, studying these features in the spectra and in the light curve, we try to understand what is the progenitor that came from that create that event. So typically for type 2, just to give you an hint from the simple matching between the progenitor and the supernova. Type 2 are linked to the evolution of red supergiant. There are some exception in the history among all the supernovae known. Indeed, for instance, the 87 supernova 1987A is a sort of a class by itself. Anyway, just because its features are not quite common to all supernovae that we know. And indeed, it's believed to, even though it's classified as a core collapse, so a supernovae from the evolution of a single star, it is believed that that kind of supernovae does not come from a red supergiant progenitor, but from a blue supergiant. The other classes, by the studying of the features in the spectra, for instance, the presence of a narrow line of hydrogen, or the fact that it is extracted a non-negligible amount of calcium in the spectra, allow us to have like a probability that for instance for type 1b and type 1c, the origin are linked to the evolution of Wolf-Rayet stars. So stars that have lost the outer envelope. So these two plots are interesting because I try to summarize all the knowledge we have now up to now on the connection between the stellar evolution of a single star and the kind of supernovae that we see, and the kind of the compact object that will derive from the supernova explosion. There is a gap in this plot in which we don't have any expected remnant, because in that range, in that region, is expected to fall the peristability supernovae. These kind of supernovae, there is no observations of a supernova of this kind, but they are expected from the theory, and are supernovae that won't leave any compact object. The peristability supernovae will just destroy all the stars, leaving nothing but dust in the region where the supernova happened. However, no supernova of this kind has never been seen. So it's still on debate that if this is a real channel of explosion for the from the observative point of view, or is just a theoretical scenario. Just if there is something else I want to add on this plot. As you can see, there the type 1bc there in the plot on the left is color coded by green and purple. Overlap more regions in the area in the plot of the right. So while type 2 are typically connected for most of the overlapping region to the formation of neutron stars, type 1bc are still in a region of balance. So type 1bc can either form a stellar black hole or a neutron star. However, again, for most of them, this connection is just theoretical because we cannot up to date have an actual observation of correspondence of the supernovae and the compact object from that supernovae. So statistically, what we can say, we can study the connection between the stellar population to this distribution of supernovae, just counting how many supernovae we can of a specific kind we have in a region on the sky. This is the theoretical expression of the supernova rate. On the left side, we have just a ratio. So the number of supernovae with respect some value that can be the volume that we with respect the volume that we scan in the during the survey. While on the right side there are the let's say the model part. So we have the star formation history of the host galaxy that of course can be extrapolated from the observations, fitting the set and all the models that we can use to study the host galaxies. We have the time delay distribution that is the time distribution between the first stellar burst to the explosion of the supernovae. So it can be easy to understand that for very massive star, this time delay distribution is a Dirac distribution because massive star evolve rapidly with respect low massive star, and so with respect the entire duration of a star of its main sequence, the post main sequence evolution is very fast. So for core collapse is almost a delta distribution. Whereas for type 1a supernovae, this is different because they come from a binary system that has to have the time to evolve to form the white dwarf, and then ignite the process to explode as a type 1a supernova. And K is just the efficiency of the event. So the efficiency for unit of mass that a star became a supernova. So just to give you an hint on how this is done, this is just a project I worked during my PhD. The project was called SUDARE, so Supernova Diversity Rate Evolution. We observed two areas in the sky, so the using the VST. These two areas of sky was the cosmos, the cosmos field and the Chandra Deep Field South. We just counted the supernova that we saw in the 4 years of surveys in those fields. This is the workflow we followed to discover a supernova. What is done is just ideally very intuitive. So it's an image difference. So you have a reference image that you took like as a template before you start the survey, to which you compare all the images that you gather through the survey. Of course, the idea is that the seeing and the PSF of the two images are similar. Then you just subtract the science image to the reference, and what remain is the supernovae, or everything that is variable. So performing a multi-epoch analysis of the sky, we extrapolated the light curve, and then we compare the light curves to the supernovae that we know. And using the light curve, just light curve to classify them. By this kind of identification and classification scheme, we were able to number the supernovae and to follow them in redshift and for specific star formation rate. The difference in the rate with respect to the type, so if a core collapse or a type 1a, depends on the type of the progenitor that we are considering. And as you can see, for the core collapse, there is a not matching at all with the models. Typically all the data it's not down number, so the values are lower than the expected, and this is because this can be because the model is wrong in predicting the number of progenitors, or we cannot see the progenitors for a number of regions because there is too dust, so the progenitors lose too much of the envelope during the evolution, and we cannot see the optical radiation when supernova explode. And just to go through a single object study, this is a supernovae that which, you know, I'll go very fast on that. Which interesting feature is the fact that apart of this, each in the decay tail, it shows some variability features that was not expected, because the decay should be just driven by the radiation decay from the nickel. However, performing a Bayesian analysis on the periodicity, we could extract the period of the orbits, considering that the variability in the tails was due to the presence of a binary system survived to the explosion. And we could confirm by the analysis of the H alpha line. The modeling suggested us that could have been the presence of a neutron star survived in the binary system from the explosion of the supernovae. And by the analysis of the bolometric light curve, we could extrapolate the features of this neutron star. So basically a very high magnetized neutron star with a spin period of 2 milliseconds. That is in agreement with the distribution of the neutrons of the galactic neutron star we studied. So just to conclude, what's next? There are so many questions that we still have to answer, and we need more computation power to perform the simulation. For instance, if we want to simulate, to include in the model the effect of a binary in the evolution that go through all the phases, and understand how the binary system influence the supernovae observation that we see, and also to in the in the era of LSST and these new generation telescopes, the amount of data that is expected to analyze is very high. So in Naples, we are developing a data center. These are the features of the data center. I don't know how much time I have left, so this is my last slide, and thank you for the attention. If you have any questions, I'll... Okay, so just I don't know how much interest there is in the specific of the data center, but we have a lot of GPU and GPU, and ideally it's open to everybody needs to have some storage or some calculation capability. And I know that I was fast on the last part, so if you have any question, please ask on all the of everything. If I'll be able to answer, I'm happy. Thank you.
So, questions from the speaker.
I have one. I really didn't get the point. How could you constrain when start seeing videos from your specific observation?
Because in the volumetric light curve, the last part, so the very late declining, it just powered by the neutron star energy. So inject the neutron star is a source of energy for the light curve. So modeling the declining using the models from the neutron star, I can use the tail of the light curve and to constrain the parameters, trying to reproduce the light curve decay.
You are assuming the classical.
I'm assuming a lot of things in this model.
Classical pulsar.
Of course. Yes.
Okay.
The idea is that is very simple. If there is something believable, I can say maybe we could have a neutron star in that region, and maybe if we wait, if we are lucky, we can go observe, I mean, in X-ray or radio and try to see something. It's not easy because, for instance, this is an interesting case because it's from 2015. We had enough data to extrapolate the variability in the light curve. And now we are 10 years from the discovery, so maybe something could be seen. We are not sure. We are in X-ray, and we are sure because the ejecta is still like expanding. So the neutron star is still not just as visible as could be the neutron star in our galaxy. And then there is also the fact that the neutron star is not resolvable. So you have to look into the galaxy. It's this specific supernova is not too far.
Yeah, what do you mean by too far? Because
yeah, it's not far with respect. Now it's too far for everybody here, but because it's like 20-ish megaparsec. But we did some calculation, and if there is just one hope, it would be like a treasure to see something. But I mean, that's what we have. That's what we can.
In principle, you can use it as an electric probe to find the pulsars in
yes, it's
region on
the what is very interesting that the the classical circumstellar material models cannot reproduce neither the peak, neither the evolution of the tail, while the highly magnetized neutron star scenario is able to reproduce the peak, sometimes miss to reproduce the rising, but most of the features of the observed light curve are reproduced by that kind of model. But it's a model, so any kind of model could in principle reproduce your data. So you cannot, is a indirect proof, but I would not say there is a proof.
Can an object like this be also relevant to explain past radio rules?
Uh, it's high, but it's not so high. Now I'm extending this specific work, studying more type 1bc supernovae from the archive, and some of them shows a magnetic field that is higher of couple of order of magnitude. So in principle, like Wolf-Rayet stars, because this is what this is in principle what we are saying with this analysis, because type 1bc is believed to come from Wolf-Rayet stars. Wolf-Rayet stars recently in a work published in last August on the analysis of Wolf-Rayet sample in the AWACS field, I guess. Anyway, they saw that almost 90% of the Wolf-Rayet in that field were in a binary system. So it's like the fact that there is a binary evolution and not just a single star evolution influence not only the evolution of the single star, but also what we can have after the supernovae. Because this kind of supernovae are related typically with the analyzing them with these models are related to very high magnetized neutron stars.
I have a question towards the last part. So you said if anyone was interested, etc. But how do you access this system? Is it to Iskra, to something?
It's still under developing. Now it's very embryonal, the data center, but we expect in almost 1 year, 2 years at maximum to be fully operative.
This would be like for archival storage, not for computing.
Both. We will have like a part dedicated to the storage. Indeed, actually, you know, in the I won't be very strictly on time, but very soon we will host all the VST image, also the archival image, because the storage they will pass from the Deutsche system to the Italian system in Naples. So we will have the archive of all the PPST data from now on. And also we have like a very important computing power that can help with the computation. Not the entire system will be accessible, so there will be like a very huge part dedicated for the university, but there will be a part of the data center that under request can be shared.
Any more questions? No, not even online. So, okay, thanks.
Thank you.